Welcome back everyone to section 3.3, where I would like to give you an overview of common semi-classical techniques. This list is not supposed to be complete, but I think the most common approaches to semi-classics should be covered. So the first approach was the one that historically was the first, and that is Ehrenfest's approach. What I would like to call Ehrenfest theorem approach. While this has been made rigorous, so for example, there's a work by Gero Friesecke and Mario Koppen from 2009. This approach is a bit unusual mathematically because it's a little bit hard to verify or to quantify the error. So this is, I think it is fair to say that this approach is not commonly used. So what is the idea here? Well, the idea is that the expectation values of position and momentum approximately obey the classical equations. So the crux of the matter is, as we have seen, is the equation for momentum. So the equation for position, at least for a non-relativistic scalar particle, works just fine. So the time derivative of the expectation value of the time-evolved position operator is just, if I introduce the mass back and the factor 1/2, it's just the momentum divided by the mass of the particle. So this is perfectly fine, but the problem arises if I look at the equation for the momentum. I can compute this exactly. So this is just the time derivative of the expectation value of the momentum operator with respect to psi. Keep in mind that the time evolution contains an epsilon here. And just by explicit computation, you can see that this is minus the expectation value of the gradient of the potential evaluated at the time-evolved position operator. And the crux of this approximation is that whether or not, so this is the step that you would have to prove, is that this is approximately equal to minus the gradient of the potential evaluated at q epsilon, at the mean position of the wave packet. So this here is the step that needs to be shown. Now, of course, if I just write approximately equal to, what I would also have to show is the size of the error term. I would have to quantify it. And what you would like to do is you would like to add an error that is of the form epsilon to, let's say, the power alpha, where alpha is some explicitly known constant that is greater than 0, because if it were 0, then this is not an error at all. So these are the two things that you need to concern yourself with. All right. So this is the first approach. Since we've discussed it in detail, I don't think I need to say anything anymore. Tightly related to that is the wave packet approach. So there's a reason why I split it up, even though wave packets arose naturally in the discussion of Ehrenfest's theorem, and that is because wave packets are treated with not with the Ehrenfest theorem usually, but with other techniques. So first of all, let me clarify what a wave packet is. A wave packet that is a normalized element of your Hilbert space that is well localized in position and momentum space. Of course, this is still a bit vague because what localized means, I mean, there are many ways to characterize localization. You could think of exponential localization, polynomial localization, a weaker notion of localization, let's say in some L2 sense. But once I show you the grandfather of wave packets, Gaussian wave packets, I think it becomes clear. So so let's think of a Gaussian wave packet. And of course, there are more sophisticated variants here. I'm just thinking of the simplest one. So here the Gaussian wave packet psi of Q naught and P naught at position X is given by, well, first I have a normalization factor. So this is a little bit boring but necessary. So this is just a normalization. And then I have a shift in momentum space. So here the mean momentum of this wave packet is P naught. And then I have to say what the position in real space is, and that's just, as the notation suggests, just Q naught. And importantly, and this is really a crucial point, is that the width is not epsilon, but square root of epsilon. So I will explain why this is important in just a second. Let me just explain in what sense you could prove a semiclassical limit. So here, this Gaussian wave packet is localized at the point Q naught, P naught in phase space. So for simplicity, I'm in one dimension here. And the one way to formulate the semiclassical limit would be as follows. And that is, if you look at, if you start at time 0 at Q naught P naught, or let's say in quantum mechanics, you use this as your initial state, then the time evolved state, which is equal to e to the minus I t divided by epsilon h epsilon, applied to psi q naught p naught, is equal to psi of q of t and p of t plus an error of order epsilon to the alpha. So of course, q of t and p of t are the solutions to the classical equations. And of course, the trajectory must start at q naught and p naught. I mean, this, I guess this is clear from the notation here. So more explicitly, they satisfy q dot of t equals p of t divided by m, and p of t minus Laplace of the potential v. So this would be roughly the statement that you would like to prove. And there are several different ways how to prove this. I will talk in more detail about this approach in the next section because it is so important. So this is a fairly common approach to semiclassics. And the width, the reason why the width is square root of epsilon, in some sense you can think of it like this. So a spatial scale of square root epsilon, or in the right units 1 over square root of epsilon, that's big on the microscopic scale, but it's still small on the macroscopic scale. So this is like an interpolation between the two scales, and so you see both. And of course, if you have this in a Gaussian, you know that the scale in momentum space is the inverse of the scale in position space. So also here, this will match up. All right, so let's go to the next approach, and that is the so-called WKB approach. So the idea is to solve the Schrödinger equation for a particular type of wave function. So this is here you have an ansatz for the wave function. Namely, the wave function, the amplitude of the wave function varies on a different scale than the phase. So the amplitude is assumed to have an expansion in epsilon. And the phase might also have an expansion but importantly, it varies quickly compared with the amplitude. And roughly speaking, the idea is as follows. What you do is you plug this ansatz into the Schrödinger equation. Then you order the terms in different powers of h bar. Sorry, not of h bar, but of epsilon. And then you solve these equations order by order in epsilon. And of course, the secret here is that these are coupled equations. So the point is that in order to solve order n plus 1, you need to have solved all the equations to the order n, because the coefficients up to nth order will play a role in the equations for order n plus 1. And this approach has been successful, for example, also for nonlinear problems. So, for example, for the nonlinear Schrödinger equation or something like that. And this has also been applied to periodic systems. And I will give a reference in the packet of references. So the next one, or rather the next two in a certain sense, are the approaches that I'm most personally involved in. So I have a natural bias towards them, but I think they are still, there are technical advantages, and they are probably among the most developed here. And this approach is with Weyl quantization or Weyl calculus. So let me just explain why a quantization, so even if you don't know what Weyl quantization is, but let me explain why quantization could be an essential ingredient, or one way to formulate semiclassics. And then formulate the statement, the so-called Egorov theorem, and then for the details, I just ask you to wait a little bit, because we are going to talk about it in the next section. So quantization is a mathematical map. So let me call this op, that maps functions onto operators. Of course, the functions have to be suitable, whatever that means for the moment. But for example, it should map the classical position Q, which is an observable quantity in classical mechanics, onto the position operator, which in this case, if we include a small parameter, is epsilon x hat, and it should map momentum onto the momentum operator, which is just minus I gradient. But of course, this also has to hold true in some general sense. So how could this be used to solve the problem that we're interested in? So f is a function on phase space. and that is a classical observable. And furthermore, let's assume that phi epsilon is, so this is a capital phi. This is not the potential, but this is the classical flow, or perhaps semi-classical flow. So it is the flow to the Hamiltonian equations of motion. And for good measure, we could also include a magnetic field. And we might even introduce some order epsilon corrections here if we wanted to. That's why I put an epsilon here. So this means that I might include these epsilon corrections. So the flow is, of course, gives the classical dynamics. And if we assume that the flow does not destroy the property of quantizability, then we can formulate the so-called Egorov theorem, or an Egorov type theorem. And that is as follows. So we define the quantum mechanically evolved observable Of course, I'm excluding all the technical assumptions that are necessary to make this rigorous. I will just give you the structure. So I'm looking at the time evolution of the quantization of the classical observable. And I'm also defining the classically evolved observable, which is the quantization of the classically transported observable. So now both of these are operators on my Hilbert space. I can compare them, and the natural way to compare two operators is to use the operator norm. Then under suitable technical conditions, on, for example, but on F, on H epsilon. So here it is important that also the Hamiltonian is the quantization of a classical Hamilton function, and perhaps the fields, so the magnetic field B, then to any fixed t, the following holds true. I should move this so that this is not covered by my beautiful face again. So we can just take the difference between the quantum mechanically evolved observable and the classically evolved observable. And so this here is the, for example, the operator norm. But you can also think of different norms here. Then this is equal to order epsilon to the n, where n is typically 1 or 2. And this is for all times from the time interval minus t to plus t. So the core of the Egorov theorem is this statement here. Let me color this so that you can see it very, very clearly. This is the core. And you see that even if you don't know what this quantization procedure precisely is, if you had such a procedure, you could at least try to compare the quantum mechanically evolved observable with the classically evolved observable. And what is nice is that you immediately get a corollary, and that is a semi-classical limit for states. You just take expectation values, and then you use the Egorov theorem to make your approximation, and that's that. But one really, really crucial thing that I think sets it apart from the previous approaches is that the validity of this does not hinge on me choosing particularly nice semi-classical states. So this limit holds for all states. And that is simply because, when you compute the operator norm, you're taking the supremum over all normalized states, and normalization is not really a crucial issue here. So you're really imposing something that is much or proving something that is much stronger than what you would with the other approaches. So if you can prove this, then you're in good shape. And let me close with the last technique, which I will not explain in detail because it is at least conceptually and mathematically closely linked to Weil quantization, and that is coherent states. And here you're taking a point of view that is dual to Weil quantization. So with Weil quantization, you quantized observables. So here you quantize states. And again, you could expect something like generalization of Gaussians. And you would have to deal with things like over complete bases and so forth. But mathematically speaking, this is something that is dual to while quantization, and that's why also many of the techniques are the same. But I will not explain this in much detail, because the most useful approaches for periodic systems, or the ones that I've seen being used, are while quantization, the WKB approach in a few works, and wave packets. So in the physics community, the wave packet approach is the most common, and I think by now, mathematically speaking, in the mathematical physics community, I think while quantization has proven to be the standard tool, and that's why I will only give details of these two approaches.